that a lot of the ideas that we're going to present are actually based on the work of Dr. Rob McDuff from ASU that I spent many hours talking to in order to get some of his take on things. I have taken some of it and implemented it in my class, and it has been really helpful to helping students with their thinking. And I shared it with Ariel, and then she got all excited. And we decided to do something at BCCE this last year, but we didn't get into some of the really cool stuff because we were more focused on ways we do it with modeling instruction, but there's some additional things we're going to be looking at. And it kind of is going to take you through what may, for some of you, feel like a paradigm shift. So please don't panic. It took me a while. I processed it for a very long time before it ever dared to be spoken of to another person, except Rob. So anyway, we really hope that this is something that you may find helpful in ways to help students better think quantitatively, mathematically. I prefer quantitatively, by the way.
Yeah, me.
Because they're often sometimes quite good at mathematics and not really good quantitative reasoning. There's a difference, but I won't say much to my math colleagues.
Hey,
they're not, none of them on Zoom right now.
Brenda, before we go further, can you introduce yourself?
I'm sorry, I'm Brenda Royce. I am a longtime modeler. I was thrust into teaching physics, was desperate and started looking around for a way to deal with it. Ran into a half-day modeling thing locally from someone locally who had been to a workshop. And it was like, yeah, that's it. That's science. That's science. I came out of laboratory settings and into the classroom. So it was really, really cool to see what modeling did, and have been doing workshops for, well, first one was in 2000, so you can figure that out. And
that was last year, right? Like 2 years ago?
Yeah. And also had the privilege of being a part of the team that developed the chemistry curriculum materials. And so anyway, go ahead, Ariel, introduce yourself.
Hi, I'm Ariel Serkin. I teach chemistry. I'm currently at Cambridge Ringe and Latin in Cambridge, Massachusetts. And as I always tell people, yes, I walked through Harvard University to get to work every day. No, you can't pack, you can't have it yet. They won't allow you, they'll kill it. Yeah, but I have been modeling since 2016, 2015 is when I took my first workshop. And my second workshop was actually with Brenda Royce for chemistry too. I was in the inaugural class of doing online workshops. So
chemistry,
for chemistry. So AMTA has been doing online workshops way before it was cool to do so. I'm really excited to be here. As Brenda said, that we started actually talking about this in the summer of 2019, because we were going to do this type of presentation at the Biennial Conference on Chemical Education in 2020. And well,
we all know why that didn't work.
So once we knew that it was going to happen in 2022, I texted Brenda, I'm like, let's do it. And I do want to say that Brenda's on the West Coast, I'm on the East Coast, and I really am grateful for Zoom that we've been able to work together. So for those of you who know about AMTA and America Modeling Teachers Association, some of this stuff will make sense to you. For those of you who are not modelers, we're going to, oh, sorry, the cat's gonna shut off my lights. We are doing a different framework of the way we talk about things. And when we're talking about modeling, we're talking about developing conceptual models. So for more details about AMTA modeling instruction, we will make sure to do some links to AMTA as well, just to make sure there's some in our resources at the end of the slides that we're going to task for you, but it's going to be we're not going to get into details about AMTA and modeling itself. We're really going to be focusing on the content of what we do. So,
Yes. And piggybacking what Ariel just said, at the end of the slides, we have like 5 slides referring to the content of what we've been talking about, going even further than what we have time for. And we have another 2 slides of just some of Ariel and Brenda's favorite teaching resources, some of which might address some of this. So, you know, if you're feeling like, well, the slides will be available to you. In fact, Erica, how will that resource be available? Actually, we have the QR code. Never mind. You have the QR code right there.
If I did, thank you. If I didn't set up the link right because I was tweaking things, just let me know and I will fix that for you.
We will also put them on the member website.
Thank you, Erica. And I guess I'll have to share that with Erica as well. So it is here for you. And we're really excited to get started. So, you know, we don't have a lot of time, so we're just going to go. All right, Brenda, ready to go?
Yep.
Okay. Helps when you're on the right screen. Woo. So when Brenda and I gave our webinar this summer, we did this as a workshop at BCCE, and we had our participants, which were a mix of high school teachers, 2-year college professors, and 4-year college professors. And we had them take sticky notes and answer 2 questions. In what ways do students struggle with mathematical reasoning in your course? And what does it look like when students are mathematically competent in a science course? Now, please realize these were chemistry people, so our answers are really geared towards that. And instead of having all of you do that, because quite frankly, there's not enough time, I'm a teacher, I'm sorry. I saved the sticky notes, I brought them home from Indiana, and I put some of them up here for you. And we saw really interesting things. And I just put the ways that they struggle. We saw that a lot of teachers commented that students struggled on how to use calculators, ratios, working with numbers and units, not thinking about their answer, what a conversion factor is. Where do they even start? And these are the types of questions that were fairly universal. We have some really specific things about moles and about ions. But if you take a look at most of the answers, they're pretty applicable to most things that deal with quantitative reasoning and how do we apply it in class. And that was really helpful for us because that could help us move forward.
So one of the things that we want to emphasize, because I've, had conversations sometimes in my workshops, sometimes from other places about, well, I just teach conceptually. And yet the quantitative nature of nature just is part of what we know about it. Nature, natural world is quantitative in nature, and particularly the chemical world is. And so rather than being shy of the mathematics are used to represent patterns in nature. And I don't feel like we can eliminate it from it. As I was talking to one participant in my workshop this summer, if your students are struggling with the math, then keep working with them to do it, but just use values that they can understand. So what we want to look at is how can we help students grasp this quantitative nature of the world around us.
And as we work together and developing this, one of the things that Brenda and I kept coming back to was how do we help our students really learn and apply it? I'm sure many of us as educators have had the experience, I taught this. How come they don't know it? Or we just did this, how come they're not using it like 3 weeks later? And conceptual competency is required to develop transferable skills. The reason our students struggle is because they actually haven't developed the conceptual competency. Because once they understand this, then they are able to apply it in the future. So our goal by doing this is to develop this skill and be looking at quantitative reasoning and applying it to everything they do. And what Brenda and I are going to be talking about, we use in our classes. This is not something just theoretical. Brenda and I can both talk about how we use this with our students.
It's right there. You will know to recognize that later. Okay.
Yeah.
Okay. So if
Go
you're
ahead.
not familiar with modeling, we know that a model is, what we're referring to it as a mental model that represents a physical system, where we're looking at observing nature, and then we think, oh, I think I understand what's going on here. But then we also have to say, oh, let me show you what I'm thinking. And that gives us all of these symbolic representations. Students seem to navigate the top three much better, but the bottom one is the one that is sort of the bugaboo. But it is also part of, let me show you what I'm thinking about it. How do we understand it? So going on.
And just before I switch slides,
yeah,
this is not our mathematical representation is not a or. These are not either or. They all
right.
work together. This is what for us is really crucial, is that your diagrammatic, your verbal, your graphical, and mathematical are all crucial elements to ensuring our conceptual understanding and how we're going from our physical system to our mental model.
Yes, and they often need to say the same thing in multiple ways. So
when we are looking at quantitative reasoning, we often find there are barriers all the way throughout. For example, our novice learners focus on algorithms and equations. So for my students, it was all about the density and the density triangles and what triangle do they use. And we're not going to get into that right now. I have very strong feelings on it. They think knowing means getting the correct answer. Oops. They use numbers and operations are only computational tools, and we use them with calculators. And I want you to listen to this, and I want you to hold this, because we're going to come back to this time and time again. They don't see any distinction between numbers, quantities, and relationships. And I'm going to say that one more time. They do not see any difference between numbers, quantities, and relationships. To our students, everything is just a number. And when they compare things, in our students' mind, they are limited to differences, like A minus B. So when I talk to my students, well, what is the difference between these two things? And like, oh, well, it's 3 because 6 minus 3, I know I'm not putting units in, 6 minus 3 is 3. And I'm thinking of a ratio comparison, which, oops, I think the B, there we go, is A divided by B. So we see these as are going to be our barriers.
And of course, doorways are more of how experts think and where we hope to get the kids. I'm going to go through these pretty quickly. So we focus more on knowledge structure and understanding. We focus on, you can keep going, that knowing is being able to describe, explain, predict, connect, making sense of, and that we recognize nature is quantitative and its relationships can be represented. Mathematics is not computational, it's representational. And then that these various quantitative pieces like numbers, quantities, and relationships have a place in thinking. Just because it has a number in front of it doesn't mean it's all alike. It has different purposes in our thinking. And this is one of the things that really got me going on this, was realizing, like we're dealing with density in my class right now, that they had mass, they had volume, they had density, but they really didn't see any difference between them. They really didn't. And they just were all things with numbers on them. And so the computations that they sometimes came up with were sort of nonsensical. They didn't see it when it was not making sense. So one of the things we want to work on is how do we help students actually see their thinking? So moving on. So we're gonna just jump right into these, some kind of crucial roles. And when we use the word quantity, I talk to my students and have them describe it, and we'll come up with, well, it's how much of something we can measure. So a trait. And here's where we're going to introduce something new that is not typically used. And this comes out of my discussion with Rob McDuff, where he developed a mathematical system that was actually quite effective in getting students to go all the way up into Algebra 1 by with the idea that the problem is students haven't connected appropriate meaning to all of these pieces. He would like to, one of the things he brought to my attention was students and sometimes teachers treat numbers as if they're like nouns, but they are not. So as soon as we move out of those wonderful, that's examples of, we got this many pencils and counters and other things to help students think through the math, and we go into a much more symbolic thing, that's about the point where we lose students in math. When the mind is thinking in quantities, the mind reasons well. But when we strip out the contextual part of this thinking, students start to lose it. So Rob developed this thing of, let's actually make shapes to represent quantity and show the math and the reasoning through these, how you could diagram things. So first off, here is a quantity because, well, we'll talk about it. So quantity, how much of a measurable trait? Notice that the unit would be obviously one of those squares, or could be something else, and we'll talk about that in a little bit, but it is the size of 1. I like telling the kids, un it means 1 it. Come on, Spanish speakers. It's un it. So, and a unit is the name of something. It's identifying an actual thing, and we can represent it with 1, as in this case, as a square. So if this is a quantity, we could then turn around and represent it, and students will not have any trouble coming up with, well, there's 9 squares there. And so you notice we have a number with a unit attached. The nice thing about this is that you cannot process that upper image unless you recognize something as a unit. Okay, so if we have these 9, where did the 9 come from? Okay, just pause right there.
Oops, sorry. Should I go back one?
Yeah. Here we have our 9 squares. How did we recognize the 9? And I've actually had my students in various ways. This year I did it with little bingo chips. Can you show me, put 20 chips out and show me the number 10? And they really struggled with that until they finally realized that while they could not know what 10 was until they defined what 1 was. So in comparing these, you notice I put a division line between them, because one of the roles of a division sign dealing with quantitative things is to make a comparison between things. The top is 9 times bigger than the bottom. That is actually representing the meaning of the number 9. But that same thing could be represented, Ariel can go 1 up, with this, where we say this is also 9 because we've now assigned 2 squares to be a unit. Think about this in science, how many times we would like students to flexibly look at something and not get stuck with this is the one and everything else has to come from it. Sometimes we need to focus on some other piece, like chemistry. This is particularly pertinent. There's the molecule, but then there's the atoms in the molecule, and we may need to count molecules or atoms atoms of this versus atoms of that. We need to be able to flexibly recognize what our unit is. And so this could be, I mean, I could have a 1 by having 18 squares that I compare 18 squares to. So this, go ahead and go forward. Yeah, so that is a size comparison. 9 squares compared to 1 square is the same as 9 pairs of squares compared to 1 pair. That is the number 9. So how do we define number? Going to the next slide.
Yep. It's thinking about it.
Yeah. So far, my internet's holding stable. You guys, we had like panic of the main internet was not being stable today. So a number, when you think about this, if I ask my students what a number is, they just really struggle ever telling me what that actually is. They want to write a numeral down, but it is actually a size comparison. I have a math colleague that used to be here where we had some dialogues, and his idea of a number was the length of one line segment compared to the length of another line segment. The comparison of those two was the number. He wanted it to be an abstract line segment, but I'm going, dang it, it's still a quantity. You have to put a number on it somewhere. There has to be a way to compare them. So a number literally is a quantity divided by a unit. Now then, if you just think about that for a moment, if I multiply both sides by the unit, we get a number times a unit is a quantity. It's like our definition of quantity actually tells us what a number is. The number is the size comparison between a quantity and whatever we're calling a unit. And notice, how do we use number in English? Ariel, take it away.
It's an adjective. We think, I know, I literally did this today, and everybody's eyes, including my student teachers, went, what? Think about how we describe things in English. I'll do this really fast. There is an unconscious order in which we use all our descriptions, all our adjectives. One of them is number. How many there are. A number is a descriptor. It is not, it's not something raw. It is not a thing. It's not a noun. It is an adjective. It is a descriptor.
And when we get that, it becomes very helpful for students. So let's keep moving because we got a lot to go.
So when we
go ahead.
When we're talking about our goals of science, it is to figure out those fundamental connections between them and the facets of nature. We are looking at how does changing A affect B. We are looking at if they do in what way. What causes the connections between A and B? What are the structures and what are those interactions? And how can this connection or these connections be represented? This is the goal. It doesn't matter what science you teach. This is the goal.
And by the word connection also was one that came from Rob, as he pointed out. We're always looking for how a change in this affects that. There's a connection between them. And, you know, it's a word that I now use with my students. What's the connection between them? So go ahead.
Okay. So now we're going to talk about some of these quantitative roles.
This is a diagram from Rob's stuff, but he would say, okay, we have a whole thing that in this case has a couple of different quantities that can be measured on it. The bluish teal square versus the blue triangle. Notice if we enlarge the size of our system, and these two are in fact connected, that relationship holds. That relationship holds. So we can put our lovely narrative statements on here that for every one blue triangle, there will be 3 teal squares. But we could also say for every 3 squares, there will be 1 triangle. In this system, 3 squares is equivalent to 1 triangle. The equal sign here, I don't say equal. Equivalent is better because it's saying these occur together. They're describing the same amount of whatever it is we have, whether it's a length of a trip or a mass or, you know, a lump of, I don't know, iron. It's still simultaneously describing the same thing. Those two things are connected. Therefore, we could say there is a relationship between them that we have just described in words in a diagram.
And I want to like call attention to that. We have our diagrammatic representation here. We have our narrative, and we're using this for a mathematical representation. All of these are helping develop that model. They're not independent of, they are all together.
Yes.
All
So
right, and let me stop
now then,
sharing.
I am going to pen myself so that, what do you mean remove pen? Okay. Sorry, it's been a while since I have done this and I need to get myself in the center of everything. Sorry. Okay, and then I am going to share a dot camera that I have so that you can see my screen. Okay, so I have a set of my little bingo chippy thingies.
Do you all see Brenda's screen?
Oh, sorry, let me share.
Oh, yeah.
Share my screen. There we go. Now you should be able to see it.
There we go.
Okay.
No,
Nope.
Brenda, we're seeing your desktop. You have shared your doc cam as your video camera.
Oh, you know what? Why don't you unshare it and I will spotlight you, Brenda.
Okay. How do I unshare here? Golly.
Top right, it's a red button that should say stop sharing, like at the top of your screen.
Oh, yeah, got it.
Better, everybody? Thumbs up if it's better. Cool. All right.
Okay.
Good. Yeah. Great.
So, I had my students actually look here. We have the same number of little chips here that we had of squares, and I may have switched. Is expressed here that within this thing, every one green thing is associated with 3 purple ones in this thing. And I asked my students, would you diagrammatically show me how you're going to figure out how many green things should be here? And by the way, I had not shown them that diagram that I showed you on the previous slide. And they think a moment, and pretty soon they're doing this. Okay, so we need to group them into 3s, and then this one goes 1, and that one has 1, and that one has 1. Okay. And we talked about, well, and let's look at how we've reasoned through this. And now you guys, I get to practice some upside down writing, so please bear with me because my dot cam shows it upside down from my view. So what we could say is that we started with 9, and I'm going to put a P here for purple.
There you go.
Okay, and then there's another fix. There we go. Now we can see more. Okay, 9 purple ones, and we needed to be able to say for every 3 purple ones, there was 1 green one associated with it. And for every means make groups. And I'll ask them what operation tells you to make groups out of something. And they'll say division. Okay, so we need to take the 9 and make groups of 3. Compare the sizes of these 2. And we notice that we get 3 groups of the purple ones, and then each of those has 1 green one associated with it. Is this like backwards to you guys or only to me?
No, it's perfect. It's perfect.
Okay, good. I'm writing upside down and reading backwards. Okay. When we think about that, we compared those 2. You guys, when we compare 2 quantities of the same type, what quantitative role is that? 9 compared to 3 gives us the number 3, it is literally a pure number. Notice we're not canceling units. We're just saying these two make a comparison, and that operation says enlarge this size by 3. So there must be 3 of the green ones that are there. So I start with a diagram and then move to how we can represent the mathematics of it after the students can explain why they did this. I had the students come up and explain what they put on their board and why it worked. And so let's go on to the next slide.
Yep, give me 1 second. And
I will.
students intuit this. Like this makes sense to them. All right.
Yeah.
So here, I feel like, Brenda, we can go on from the slide, but this is just representation. Yes?
Yes, but this is showing it from the,
right.
the little green triangles and squares again.
I forgot to change the triangles to blue. I'll change that later.
That's okay. That's all right. We'll excuse you on that.
Sorry, I apologize.
Okay. So anyway, this can be simplified. And what is powerful is once the students learn to reason this way, whatever ones you use, you'll notice there are a lot of equivalencies between quantities that this could apply to. We might be talking about density where 3 grams is the same as 1 milliliter, or a speed where 3 centimeters is what something travels in 1 second, or we have 3 joules of energy associated with 1 gram of mass, or I buy 1 pound of apples and it costs me $3. These are all using exactly the same reasoning. Okay, keep moving.
Yeah, and I want to tell you that I want to see that we're getting at the conceptual competency here. Same process all the way throughout. It's not about memorizing a velocity formula. It's not about memorizing density. It's not about memorizing a unit, like what is a unit conversion. We are looking at what is a relationship.
Yes, and this can also be
apparently we said this
yeah,
here too.
teaspoons. Yeah, all right.
Okay,
so,
this is the goal.
So if you'll notice, modelers will recognize, we go from experience, we do through some kind of visual representation, we start describing it, and then we move to symbolic. And I think this is one of the most important things we can emphasize is that too often we show students the symbolic before they've developed these middle pieces where they have a way to actually think about it. Keep moving. So in physics, any physics people out there, you'll recognize the little buggies, and we could turn this into a motion map. This allows students to translate their data into something that says this began here and moved this far every second. This is a visualization of it. Okay, and then we can say, oh, but every second that passed, the car displaced by 3 centimeters. And we can see that cumulatively, we end up with, by this point, in 3 seconds, 12. This is in a way that this could be diagrammed. Okay, and then using the verbal, every second the car moves in the positive direction, it will change position by 3 centimeters. The elapsed time doubles, the car's displacement also doubles. Ways to describe this. So from 3 to 6, in 1 second versus 2 seconds, we go from 3 centimeter displacement to a 6 centimeter displacement by doubling the time. They can see this.
And once again, we are seeing the different representations are actually showing your conceptual understanding. And I know I'm going to say this 15 times. This is not just about throwing things into a formula triangle. This is not just about getting an equation. This is really about showing your understanding.
Okay. Now, if we want to go a little further with like the physics idea is, and this is what I did when I was teaching, actually before I started teaching 9th grade physics for a while. I turned the motion map up on its side. It became my position axis and had the kids translate this over so they could see how that fit on the graph. still saying the same thing. For students who don't get what slope is, this can help also understand that we have a regular change every second. There's a displacement that we saw in the motion map, and this line is simply spreading things out over time. Anyway, how do we translate that into something mathematical? Well, we have the same idea that when it, say, travels for 3 seconds, we can use the same reasoning. Well, that's 3 times bigger than the 1 second in the relationship, so we need 3 times the displacement. We keep going. We have a n equals 3 when we look at that, and that gives us, you're gonna have to click several times here.
Oh, yep.
3 groups, 1 for each of the 3 seconds that went on there. So 3 groups of 3. I'm sorry, there's too many 3s in here, but so we translate that the change in time can be multiplied by this relationship between position and time, and it gives us the quantity of the change of position. Now, I realize there's an initial position that physicists often want in here. We can, if you want to talk to me, there were some ideas about that. Scott, you can talk, maybe also Scott Milam in the group was talking with his physics teachers about this, but notice, we start with a quantity that we know, we use a known relationship, and that lets us find another quantity.
And I'm just gonna quickly hopefully not. Look at that. Your quantity
Letter.
times your relationship is going to equal your second quantity. Just
Okay.
if you're taking notes, it's a good thing to do.
Okay, I think we're on to.
Yep, I just needed to clear it to go into the next slide. If it'll let me. All right, models of chemical reactions. For the chemistry people who are here, I know we have some chem folk, is that we know that hydrogen reacts with oxygen to form water. And thank you, Brenda, for including our diagrams here. And for those of you familiar with water, there are 2 hydrogens for every 1 oxygen. And what we can see is that as we group it, we can get how many hydrogens and how many oxygens do we need to produce that water. This is a way of, as you are beginning to work on balancing chemical equations, you can already begin to work in some initial thoughts about stoichiometry and limiting an excess reactants just by looking at how these quantities and these relationships combine. So we have those 2 hydrogens combining with that 1 oxygen, circling your groups. There we go.
And we can see by the fact that we can do this over and over again, it's for every 2 moles of hydrogen.
So for every 2 moles of hydrogen, 1 mole of oxygen will also react to form those 2 moles of water. And so when that number of hydrogen used up doubles, you're actually going to see the same thing with a number of oxygen. That's going to double, and the number of water molecules are also going to double. So you have that consistent relationship all the way through. It's not just about in one group, it's about applying it throughout. We're seeing the quantitativeness of these relationships that is inherent in nature. And we can use this moving forward when we begin to look up. So for every 1 mole of oxygen and 2 moles of hydrogen that react, we form 2 moles of water. So our N equals 2. That number equals 2. So that means, so if we double our amount of oxygen, I have to remember what things we have here, so that if we have, so let me back up a bit. I know that I need 2 oxygens. There's 1 unit of oxygen, that diatomic, for those 2 forming 2 water molecules. Well, what happens if I have 2 of those
The molecules?
the molecules, thank you, words, of oxygen? Well, then my amount of water is going to double. So 2 moles of, so we see it there. And for those of you who are familiar with our BCA tables as a way of looking at stoichiometry, here we're showing that quantitativeness this way. We are not going to spend time here going over our BCA tables. They're brilliant. They're wonderful. We're not doing them right now. We'll save that for another time.
Yeah. Yeah,
But
but we do want to, yeah, go ahead.
go ahead, Brenda.
I was going to say, what we do want to show you is, here is a way to visualize the reasoning in a, in a simple setting where students can say, oh, I have a certain quantity of one thing, and this is representing 2 moles of oxygen when we put the 2 molecules of water over here. And every molecule of oxygen will be able to form with enough hydrogen 2 molecules of water, helping students visualize that this is what the pieces they're putting into their calculation mean, so that they have a concrete quantitative view of what these math symbolic things and chemical symbols mean. We could have done this with dots. I really don't like using the little dots in chemistry because the circles mean something else in chemistry. So when I have the chance to actually diagram, atoms and molecules, you might as well just diagram them. It's what we're talking about. So anyway,
Sorry.
So this is a way that honestly we do in fact use in order to help students understand. So what we don't have time to discuss right now is what relationships might you have in your course that you need to make conceptually clear. I would encourage you to be able to write a for every statement, doubling language thing for it, but also, is there a diagrammatic way that you could come across showing this? You can see my screen at all.
Oh, hold on.
We were doing this.
Hold on.
We were doing this on today in class by diagramming
Let me just-
density, by having them look at, if I had this much mass and I was using a circle as one unit of mass, they were working with the little chips, and you group it according to the density that you have, how much volume would that be? And they literally formed all the groups and then drew the boxes around it to show how much volume there was. And after they had done that and they knew what the answer was, then they set up the calculation and related that back to the diagram that they knew was right. So they could see why this needed to be set up the way it was. So
And
we can unpin
Actually,
me.
no, I'm not going to unpin you, because if you see written on the board behind Brenda, also I always like looking at Brenda. Looking at the board behind Brenda, you see Q1 times R equals Q2.
Yeah.
A quantity times a relationship equals another quantity.
So the
And
role of,
go ahead, Brenda.
I was just say the role of the relationship is to serve as the connection between those two quantities. Quantities are the things we can measure. This has to have both parts. And today we were going around making sure people actually had 2 parts to their relationship, because many of them just put down 7 or 4 or 2 and like, we're done. It's 2 times bigger. And I said, but if you multiply 6 milliliters times 4, you don't get 24 grams, you get 24 milliliters. What? So you could just see the look on their face. It was just like, what? Until they realized that you had to do, that's not what they did up there with their little chips. They actually had to take the volume and figure out how much mass went in each one, or take the mass and figure out, is it his on the top, 28 grams times, they had to figure out, oh, they had to make 4-gram groups, and then each one of those they assigned the volume of 1 milliliter. Just, I could see a much clearer look in their face from doing this than when I would allow them to just use a formula they could plug things into.
And my students,
even I was gonna say,
ahead.
even though they developed that calculation, even though that came from their graph, they still, yeah.
So our students, I will unpin you now, Brenda, so you don't have to feel like you're in the spotlight.
Whatever.
So our students, many of our students will come in wanting to, what formulas they have to memorize, and they get stressed about that. And by looking at it this way, what we see that it's not about the formula. It's about developing that quantitative reasoning and about looking at a relationship between our quantities, our relationships, and our numbers. We, as experts, intuit this. We understand this. And what we are doing here is we are making that thinking explicit so our students can then go ahead and apply it. Quite frankly, and like my high school chem classes, Q1 times R equals Q2 is pretty much what they need to know all year. And as we develop vocabulary together, we can say, is this a quantity? Is this a relationship? What does this relationship compare? And Brenda and I had all sorts of conversations over the summer. Really, they lasted hours, about how we could use this and how this could help our students, especially those that don't have the mathematical confidence. And we can apply this going forward. And I'm going to share back our Aaron's quotes.
Ariel, can you check the chat? Oh, I see that Brenda got it.
Yes,
Okay.
Jacqueline brought up an interesting thing of finding a relationship between bonds and which items in the DNA were cross hydrogen bonding. And yeah, if you can find the relationship, then you can. So the trick is now, how are you going to represent it so that it gets across to the students? But anyway, Aaron's, Lawson. So it found this very interesting, was reading Aaron's, and Lawson was quoted in there. And this is Lawson of the Lawson's proportional reasoning test, a reasoning test.
And you need to say who Aaron's is, because although you assume everybody knows.
Well, Aaron's is the author of a book, teaching
Introductory
physics.
Introductory physics, I believe.
Teaching introductory physics, and amazing stuff in chapter 1. I think every teacher who teaches anything quantitative should read chapter 1. But
I might have linked to it.
Yeah, a necessary condition for the
Sorry.
for the acquisition of proportional reasoning is, interestingly, that they have to have key linguistic elements, the ability to make an argument. Think about the ways we're putting the narrative phrases in there, using the phrases. When something doubles, what happens? When, for every so much of this, we have so much of that associated with it. And Aaron's, man, teachers who have mastered arithmetical reasoning, and I would substitute quantitative reasoning, sufficiently thoroughly to lead pupils into articulating lines of reasoning and explanation in their own words. And this is goes back to a key thing that comes out of Dave Heston's idea that not only do we need models, we need really good student discourse. So having a basis for diagramming their thinking, I think, really helps students. And being able to articulate it based on diagrammatic things may replace some of the lost stuff that came from when they got yanked out of good, concrete, quantitative reasoning into very symbolic, abstract, mathematical reasoning with too many symbols that they didn't connect to a concrete idea. So, you guys, have you ever thought of trying to reason it entirely in adjectives? Ever tried to think of communicating purely in adjectives? If numbers are adjectives, no wonder kids have trouble when we strip it down from quantities that they can grasp to adjectives that somehow form a pattern. Yeah. Anyway, basically, this is what we have.
And we know
we have a little time for some questions.
Well, before we get to the questions, and we've said this 3 times because this to us is a big deal. This is the goal. First of all, I think the QR code links work. So if you do not come at the beginning, here's the QR code that you should be able to get the slides.
That was Olivia who helped us get things set up at BCCE.
At BCCE,
we were so grateful.
We love her. She made it happen. But I want to highlight, we're not going over them. These are resources for you because we talk all the time. This is all we think about. Brenda has given examples of, this is Brenda's brain dump of the story of how this works. So this is the TLDR version. Too long, didn't read for those of you who don't speak. The stories, how these things fit together. Examples of how they work. This is Brenda's favorite physics example, just letting you know. And what we have here are some of our favorite resources, including the AMTA website. It is there. You need to know it. It's there for you. It is some science works and then some of the articles that they're linked to. So the one that I'm asked about is about Rob McDuff. If you look here, I've linked to it, and if you give me some time, eventually I can go actually make more of these hyperlinks because I have a lot of McDuff's article is here for you to read.
It's a website. I will say he tends to not what he's done here. He's moved on to some other things. So this is sitting there in a much streamlined sort of fashion, but if you want to look at it, it'll give you an idea of where some of this diagramming came from.
And some of these are journal articles, some of these are websites, some of these this is our favorite, but this is not relevant right now. All right, so I'm going to unshare the screen. I'm going to put the link for the survey in the chat. And if you would like a certificate of attendance, you have to. All right, we've talked for almost an hour. I'm sure your brains are spinning, but we have a few minutes for questions. Oh, absolutely, Chris, no problem. And if I screwed up the QR code, please forgive.
It works. I checked it. It does work.
Thank you. It was not that I don't know how to do QR code, but I had done this summer and I didn't know if I updated to the right one. Hold on, it's being temperamental. All right.
We know that, as we said at the beginning, that was a very massive, very possibly a fairly massive shift of thinking and ways of thinking, or maybe not. But do you have any questions for us?
No. What questions do you have?
Yes. Would you put them in the chat? Would be the easiest way.
So Jacqueline had a question about students who she has in college who do not have basic understandings of math. You can, if you want to scroll up, she has a couple more statements.
Yeah.
Yeah. So Jackie, that's a really cool question. So I'm going to read the question out loud because that's good practice. So Jackie teaches college students. Full disclosure, Jackie and I are college friends. And her own kids are middle schoolers. I can't believe that. And they're also using this way. Do we see students starting to come in with this line of thinking already? And do we see student understanding based on how they learned it from the start? Brenda and I have really different populations of students also, which is interesting. I will say with my honors classes are going to be still very algorithmic heavy. That's how they learn, that's what they want. And I push them and makes them grouchy. My general chem students have internalized fear of mathematics. And this type, so I don't know, Jackie, if they naturally think about it that way, because as they get to the upper level maths, I think it starts changing in middle school about how it's approached. This is not a critique of math teachers, but this is my experience. And so then they come in knowing they can't do math, and showing it this way, it actually reduces their math anxiety.
Yeah, I have quite a mix of students in the sense that well, I'm teaching honors chemistry, but I have students who are very math shy, and by today we're working, some of those students were probably for the first time seeing a connection between the symbols they were writing and the meaning of them, because it was in their face on a little whiteboard in front of them. They had done it. And I would just ask, remember, it's one student, well, what did your diagram tell you? How did you do that? And we have to translate it. Someone else asked, was it Jeff, about how you kind of start this. I kind of like we did in introducing the meaning of some of those key things, like what's a quantity, what's a unit. We do that right up front so that when, well, not right up front, but fairly soon, particularly right after they do one lab where they've already been doing things. And then we say, now let's understand what we've been doing. You know, what's a quantity, what's a unit? We talk about it, we define it together. And I don't go jump straight to number, but that comes very soon after because they need to process it a little bit. And then it is simply something that I come back to every single time that you use anything quantitative. In the modeling chemistry, that means unit 1, unit 2, unit 3, unit 5, unit 8. But I'm diagramming reaction ratios and such in unit 7, still diagrammatically showing what those values mean. Now, here's the fun part, is that when I start asking the kids, well, this thing we're looking at, is this a quantity, a number, a unit, a relationship? And I expect them to be able to tell me. And there's, when I first started doing this, we got to describing a chemical reaction. Even before I started diagramming it, I just asked them, are these coefficients numbers, quantities, units? They had a bit of a debate and finally came up with, well, this has to be a relationship. In other words, does this tell us how much we have? Or is this telling us something about some connections in nature? And so you know, like so many things, you introduce it, you give some foundations, but then you really teach it all year long. This is something that isn't just do it at the beginning. It has to be part of the dialogue for the rest of the year before some kids will actually buy in that, oh, this is meaningful. This is meaningful. And by the way,
go ahead.
I would say one other thing. One of the ways I keep from getting in trouble with my math colleagues is, and I think it's very true, I tell them scientists deal with something a little different from math. Nature puts constraints on things in ways that math doesn't. We don't deal with anything really abstract in the sense that anything could be possible. We don't have non-real numbers, you know, and even some of our quantities have limitations. You can't have negative mass. Some things will only be in the first quadrant of the graph. You can't subtract certain things. You can't add certain things because of what they are. There are constraints. So I'm teaching you science math. And then mathematics. I love math. I did, honestly. What you're doing in your math class is about abstract number math. We're doing science math, and then I don't get in trouble.
I want to call just attention that we are respecting your time. It is of the hour. For those of us on the East Coast, it is 8 p.m. For those of us on the West Coast, it is 5 p.m. Wherever you are, you need to figure out your own time zone. If you have, I can't keep track, especially still daylight savings time for some of us. If you would like, you have our email addresses if you got the slides. If you know me and Brenda, we're happy to talk with you later on. We can stick around for a few more minutes. There will be a recording available for AMTA members, and the slides will be there. And spoilers, stay tuned for science modeling talks. Am I allowed to say that? Too late, I already did.
Yeah,
Great.
we will.
I will say, okay, I'm looking and people are logging off, which is fine. Ariel, could you put that link to the survey in one more time so they have it? And again,
Absolutely.
you can
Okay.
reach out to our wonderful hosts and presenters if you have any more questions, or you can always reach me. I can put my email in the chat. If you have any questions about getting the certificate.
And
And
thank you so much for coming.
I think our emails are on the beginning of the slides, right?
Yeah, they're on the beginning of the slides and the end of the slides because we're just back at Brenda.
Yeah.
And it's
the
okay.
email's at the end.
No, they're at the, maybe they're only at the end. No, it's okay. Oh, whatever. We understand also
Are
if your
they?
brain needs time, I don't remember, if your brain needs time to process, because quite frankly, the first time I heard this, my brain, I swear it exploded. I took 4 pages of notes on a phone call with Brenda, and we have been working on this, talking about this for a while. And the thinking is there, but the application is going to take some time. And this really can be used in multiple ways. And it's
And it does make a difference in how students understand things. But you have to talk about it the way that it is. That's what, these roles and stuff. And there is more to what I do. There's just not enough time. There's just not enough time. So that survey that Ariel showed you a link to gives you an opportunity to say what additional questions. If we find some good patterns, we might do a second session sometime. We'd be willing to do that. So. Jane just put McDuff stuff, a link there that I didn't have.
Oh,
so
thanks, Jane. Jane, I will add that to the slides as well once I get to the right slide. Here you go. Cool. I'm not gonna format the, oh, nope, oh, darn it. I forgot you cannot copy from. In case you didn't remember, you cannot copy from a chat. Here you go. All right, it is not formatted beautifully, but here it is for you. And I'm impressed that Erica's child will accept homework help because mine absolutely refused to do so. All right,
hey.
I think we can stop recording.
But if anybody has any questions they'd still like to ask, we're willing to hang on for a little bit longer.
Yeah.